Microplastic (MP) have been an environmental problem worldwide since the Industrial Revolution, as plastic has become an alternative to other materials such as cardboard, glass, metal, and wood. Improper disposal of plastic has led to contamination of water bodies, soil, and the air we breathe. One method for the resolve this problem is the synthesis of functionalized nanomaterials for the recuperation the microplastic. In this project, Fe₃O₄ nanoparticles were synthesized via a solvothermal route with size and morphology control using two types of iron precursors. The resulting particles were characterized to determine their crystalline morphology and optical properties. The results showed that samples Y1, Y2, and Y3 demonstrate more defined and intense peaks indicating higher crystal quality and homogeneity compared to the other samples. Surface modification of the nanoparticles was carried out through an immersion and stirring process using TiOs and methanol. The magnetite was tested both with and without surface modification under normal temperature and pressure conditions. The removal test simulated wastewater contaminated with microplastics, 0.4 mm polypropylene, using a concentration of microplastics in tap water and different stirring methods to replicate the conditions of nature water currents. These contaminants were recovered using a neodymium magnet, 50 Gauss, measuring 4 by 4. Plastics have revolutionized modern life due to their versatility, durability, and low production cost. Since the mid-20th century, their use has expanded into sectors such as the food, medical, automotive, and technology industries, becoming an essential material for contemporary society. However, their massive production and inadequate waste management have generated serious environmental problems such as the accumulation of non-biodegradable waste, the release of microplastics into aquatic and terrestrial ecosystems, and the alteration of biogeochemical cycles. These particles affect water quality, enter the food chain, and cause significant damage to biodiversity, thereby compromising the health of wildlife and indirectly human health. Considering this situation, it is essential to develop innovative, sustainable, and economically viable solutions. This work presents a bioremediation strategy applied to aquifers based on the synthesis of magnetic nanoparticles, a low-cost material with strong magnetic properties that facilitate the capture and removal of microplastics. This technology aims to contribute to the restoration of affected ecosystems and to mitigate the environmental impacts associated with plastic pollution. Raman 214 cm 1 and 273 cm 1. These bands correspond to T2G vibrational modes of magnetite associated with the motion of Fe ions in octahedral sites of the inverse spinal structure. 3 and 81 cm 1 also attributed to a T2G mode related to the stretching vibrations of FeO bonds within the crystal lattice. 588 cm 1. This is the most characteristic signal of the Fe₃O₄ phase, assigned to the A1G vibrational mode, corresponding to the symmetric stretching of oxygen atoms around Fe ions in tetrahedral sites. This peak is considered the key fingerprint for confirming magnetite. 1268 cm. This broad band does not correspond to a fundamental mode, but rather to a second order process, 2 magnon scattering or overtones typically observed in iron oxides. Its presence is often related to structural disorder and electron-phonon interactions. The progression of the spectra A, B, C, D shows the gradual coating of silica. Characteristic psi-OC bands at 1100 and 800 cm1 appear and increase in intensity while the field signal attenuates. The presence and subsequent decrease of the SiOH 950 970 cm1 and CH2800 3000 cm1 bands indicate the degree of hydrolysis, condensation of TiOs, and the purity of the material. Conclusions. The synthesis and characterization of inverse spinal shape magnetite has been successful and has provided valuable information about its properties and the control of its morphology. Heat treatment time determines particle morphology and the formation of inverse spinal. Regarding the functionalized Y3 sample, it was shown that the better formed the structure, the better the microplastic recovery, achieving the highest recovery rate of 72.41%. Conclusions: the synthesis and characterization of inverse spinal shape magnetite has been successful and has provided valuable information about its properties and the control of its morphology. Heat treatment time determines particle morphology and the formation of inverse spinal. Regarding the functionalized Y3 sample, it was shown that the better formed the structure, the better the microplastic recovery, achieving the highest recovery rate of 72.41%. Thank you very much for your attention. It is greatly appreciated.